Welcome. My name is Alexander Moreira with AlphaStar Academy, and today we're going to be discussing the problem red-black forest. In this problem, we are given n trees and k intervals, where each interval must have at least ti trees in it. And starting with this complete forest, our goal is to determine the maximum number of trees we can chop down while obeying the constraints of each interval. So let's make the problem a little bit more concrete with an example. We're going to start with trees in positions from 1 to 7. Note, it doesn't really matter if the trees are sequential or not, because we could always use coordinate compression to make them sequential if that ends up being valuable. And then we will start with 3 intervals. So the first interval is going to range from 4 to 7, including both 4 and 7. And this 2 is going to represent the fact that we need at least 2 trees. So that's saying in this interval of trees, we need at least 2 of them to not be chopped, or we need at least 2 of them to not be chopped down. The second interval ranges from position 2 to 5, and this one needs at least 3 trees. So in this range of trees, at least 3 need to be not chopped down. And then here, our final interval is from 1 to 2, and this interval only needs 1 tree. So what's the solution here? Well, I claim that we can chop down the trees 1, 3, 6, and 7. So let's take a quick look at a visualization of these intervals and see what happens if we chop down those trees. So I'm claiming we can get rid of tree 1, we can get rid of tree 3, and we can get rid of trees 6 and 7. So what do you notice? If this is the first interval, it has 2 trees in it, 4 and 5. So that interval has been satisfied and has at least 2 trees. Interval 2 has at least 3 trees. It has 2, 4, and 5. And interval 1 has the 1 tree that it needs. So all of the intervals have been satisfied. So we get to chop down 4 trees in this example. In this video, I'm going to discuss 2 solutions. The first is a simple, greedy idea that gets partial credit with just sets, but can be extended to full credit using binary index trees. And then the second idea I'm going to share is from my colleague Osman I, which uses the sweep line algorithm. Let's begin with the simple greedy idea. In this greedy algorithm, we are going to assume that every tree has been chopped down. So we're going to be very overzealous, chop down all of the trees, and then we're going to loop over the intervals. And for each interval, we're going to replant the minimum number of trees necessary to satisfy that interval. In order for this to work, we have to loop over the intervals in a very particular order. We want to start with the interval with the largest leftmost coordinate. And I have chosen a set of intervals where we can see that the leftmost coordinates are in descending order. We could always sort the intervals to achieve this in our code. So we're going to start at interval 1, work out what are the minimum number of trees we need to unchop in order to satisfy interval 1, and then we're going to proceed on to interval 2, ask the same question, and continue. So in interval 1, we know that there are currently 0 trees, right? All of the trees have been chopped down. So then the question is, how many do I need to regrow? Well, interval 1 needs at least 2 trees, so I will have to regrow 2 trees. And I've got 4 trees to choose from. So the question we want to ask for our greedy algorithm is, what trees would be best to regrow? And the answer to this question is that it's best to regrow trees 4 and 5. And the logic here is simple. 4 and 5, because they are further to the left, are going to be more likely to help with future intervals, whereas trees 6 and 7 are further to the right, so they're going to be less likely to help with future intervals. Again, this is because I've sorted the intervals based on the leftmost coordinates, right? So this is the interval that is furthest to the right in terms of its leftmost coordinate. So this is going to be the most helpful for any future interval. So we will regrow those 2 trees, and then we will proceed on to interval 2. In interval 2, we can see that there are currently 2 trees, but we need 3. So we have to regrow one of the trees that has been chopped down. And for that, we have 2 choices, either tree 2 or tree 3. 4 and 5 have already been regrown, so we can't regrow those trees again. So the question is, which is the best to regrow? And the answer is, of course, going to be tree 2, because again, it's further to the left and therefore more likely to help with future intervals. So we're going to regrow tree 2, and then we're going to move on to interval 3, which we can see is already satisfied by the fact that we regrew one of the trees inside it already, and it only needed that one tree. All right, we're now ready to begin coding our algorithm. So we've started here by reading in T the number of test cases, and then we've defined a solution function where we're going to put the bulk of our code. We want to start off by reading in our variables n and k. As a reminder, n is the number of trees and k is the number of intervals. Now we want to read in both the trees themselves and those intervals. For the trees, I'm going to store them all in a set called chopped, because again, my algorithm is assuming that all of the trees have been chopped down at the beginning of the process. So we're going to loop over the n trees and feed each of those into our set chopped. And then we are going to work out what are the intervals. We can create a n or a k by 3 matrix to store those, where we're going to store first the leftmost point in each interval, then the rightmost point in each interval, and the number of trees that that interval requires. And once we've read in that entire set of intervals, we can sort the intervals, which is automatically going to sort based on this leftmost coordinate. So it's going to sort them from least to greatest. So this means when we go to loop over our intervals, we will want to do it in the reverse order so that we can traverse over the intervals from the greatest leftmost coordinate to the smallest leftmost coordinate. To store the unchopped trees, we are going to start with a set. It will be initially empty, and we will add trees to it as we go throughout the process. So we'll remove trees from chopped and then add them into the unchopped set. So we're going to start by looping over the intervals backwards as mentioned. So our very first interval is going to be at position k-1 in our matrix of intervals, and we're going to record L, R, and T to represent the leftmost point, the rightmost point, and the number of trees we need. Our first thing that we want to do is work out how many trees are already in the interval. So remember back when we were looking at interval 2 here, when we started the process of interval 2, we saw that there were already 2 trees in the interval. So what that tells me is that I only need to add one more tree. So one way of counting the number of trees is we are going to search for what is the leftmost tree in the unchopped set that's within our interval. So we're going to apply binary search for L in unchopped. And then we're going to look for what is the rightmost tree. So we're going to search for R. And then the number of trees in that interval is going to be just the distance between left and right. So we're going to revisit this line of code in a little bit here. But for now, it's going to return us the number of trees inside this interval in the set unchopped. If the count is less than t, then we need to add trees to our interval, right? So here was an example of that where we had the second interval. We had 2 trees already there, but we needed 3 trees, which means we had to add one more tree. And what was the best tree to add? Well, we wanted to add the leftmost tree available to us. So what we're going to do is we're going to check, is the count less than t? If this is true, then we need to add some more trees, and we're going to figure out what are the leftmost trees that we can possibly add. So to find the first one, we can apply just binary search, and then we can start counting from that point, finding the difference trees that we need to add, where difference is just t minus the count. So that is the number of trees that we're going to be adding to our unchopped set in order to satisfy the interval that we're currently on. Once we have found these 2 pointers, we can insert all of those trees into the unchopped set, and we can remove all of those trees from the chopped set. And then after this, our final step is simply to print out the size of the chopped set, and that completes the program. So just to give a quick view, this is our main function, this is our solution, and here's the top. So this algorithm almost works. It seems super tempting to use. Everything here is running super quickly except for line 31. So line 31 in C++ sets, in order to find the difference between 2 items, it has to perform a linear search. So this line 31 is what's slowing us down here. You can speed this up by transforming unchopped into a different data structure, which allows you to search faster for the distance between items. So one example of this would be a binary indexed tree. But let's talk about a second solution that does not need that. We are now ready to begin discussing the sweep line idea. So there are 3 important events that we care about in this problem: trees, the start of intervals, and the end of intervals. So our goal in this problem is going to be to store all of these events in a vector, and then we're going to loop over the events in chronological order and resolve an action for each. So there are going to be 3 different cases that we're going to have to look at. So the first case, when an interval starts, we're going to want to record the maximum number of trees that we're allowed to chop while that interval is active. So we'll add this to a multiset. The reason we're using a multiset here instead of a set is because multiple intervals could have the same constraint, right? I could have 2 different intervals that both say I can't chop more than 5 trees while this interval is in play. When I find an interval end, I will want to remove that max number of trees from the multiset, right? So each maximum number of trees that can be chopped serves as a constraint on the number of trees that I'm going to be chopping. So when an interval is over, it's important to remove that constraint so that in the future I can continue chopping trees if I'm no longer bound by that interval. And then the final type of event is when we find a tree, we have to decide, can I chop it or not? And what allows me to do this is if the number of trees I have chopped is smaller than the smallest constraint in my multiset, then I know that I'm allowed to chop this tree, so I can chop it, increase the count of the chopped trees, and then continue on with my algorithm. One thing that we're going to have to think about here is, how do I remove the max number of trees from the multiset once I reach that interval endpoint? And for that reason, we want to make sure that we're storing enough information that I can go back and find both when the interval started and how many trees I chopped at that moment in time. So let's take a look at our code. So we've got here so far just a main function and the solution where most of our code is going to go. And we're going to start by reading in all of the values. So we're going to start off just like in the previous code. We're going to read in n and k. Once again, as a reminder, n is the number of trees, k is the number of intervals. And then we're going to create a vector to store all of the trees. And we are going to create a vector to store all of the events. So let's describe what is going to be stored in this events vector. And it's going to be a little bit different for trees and intervals. So in the first case here, the first number is always going to be the position of the event. So if it's a tree, it would be the position of the tree. If it's an interval, if it would be the start of an interval, you'd store the start of the interval. If the event is the end of an interval, then this is going to be the end of the interval. The second value in events is going to store the event type. It's going to store the interval starts as a 0, trees as a 1, and intervals ends as a 2. What you'll notice is that the interval starts are recorded before the trees are recorded before the interval ends. So when we sort this events to loop over in chronological order, this means that we're going to address any interval start first, then we'll look at the trees, and then we'll look at intervals ending. So this makes sure that we're proceeding in the correct logic. Next, the third element in events is going to store the number of trees we can chop. This value only gets stored if we're an interval, right? So for every interval we're going to store, this is the number of trees that can be removed from this interval. It's going to be the total number of trees in the interval minus the number of trees we have to keep around in that interval. And then finally, the third value, or the fourth value, I should say, is going to be the other interval endpoint. The reason why we want to store this for intervals is so that when we're looking at the interval endpoint, we can always go back and recover when the interval starts. So this is going to allow us to figure out for any time we're trying to remove an interval from our multiset, where did the interval start? Great. So now we're going to continue on and actually read in those events. We're going to do it in 2 steps. We're going to read in all of the trees and record those tree events. And then we're going to loop over all of the intervals and record all of the interval events. So what you'll notice here is that we read in L, R, and T, just like we did in the previous problem. We read in the leftmost point, the rightmost point, and the number of trees that we have to keep. But we're going to make a small transition here. We are going to count the number of trees in the interval immediately. So what this does is it just counts the first tree in the interval and the last tree in the interval, and then the difference between those two positions gives us the total number of trees in the interval. And then if we subtract off the amount of trees that we must keep, so this is the total number of trees, this is the number of trees we have to keep. The difference between those is the number of trees that we're allowed to chop down in this particular interval. And then we are going to record 2 events. One event for the start of the interval and one event for the end of the interval. And then we'll sort events. Again, we're sorting based on the position foremost, but if there's ever a tie in position, we're using the event type to break the tie. So this is why it was important to store interval starts as 0s, trees as 1s, and interval ends as 2s. We care about how those ties are broken. And then we're going to continue on. We're going to store a map. This is going to be a map from tree position to the count of the number of trees removed at that point in time. So every time we chop down a tree, we're going to record the total number of trees chopped down. And this is going to help us, again, in this case, when we're trying to work out how to remove an interval from our multiset. And then finally, we want to actually create our multiset. So this is just going to store the max number of choppable trees for each interval. Before we've looked at any intervals, we're going to start with a large upper bound. We're going to assume that we can chop all of the trees until we see a constraint from an interval that tells us otherwise. And now we're ready to begin looping over our events in chronological order, keeping track of the total number of trees chopped. So this is really important here. This variable is going to store not just the number of trees chopped in any interval, but the entire count of the number of trees chopped throughout the entire process. So this will be our final output at the end of the program. Then we're going to loop over the events again in chronological order, and we are going to start with case 1. We found a tree. So what did we want to answer when we found a tree? We wanted to answer, can I chop the tree or not? And what's going to allow me to chop the tree is if this count, the total number of trees chopped, is smaller than the smallest constraint in my multiset. So the smallest constraint in my multiset, since multisets are a sorted data structure, it's just going to be the first element in the multiset. So if the event type is a 1, that corresponds to a tree, and the beginning of my multiset minus the count is positive, so this is saying that the count is smaller than the beginning of my multiset, then I know that I can chop this tree. So I'll increase my count by 1, so the number of chopped trees will increase, and I will record that a new tree has been chopped down in the location of this tree. So I will add this to my map from earlier. Case 2 is the easiest. When I'm starting a new interval, what do I want to do? I want to add the maximum number of trees that I can chop while this interval is active. And you may be tempted to just add E2, which is again, the number of trees that we can chop in the current interval. But that is the number of trees we can chop in the current interval starting from just the current interval. We actually want to record here the total number of trees that I'm allowed to chop while this interval is active. So I'm going to take the number of trees I can chop in this interval and add it to the total number of trees that I've chopped already. And that's saying that while this interval is active, I can never chop more than this number of trees. So this will provide me an upper bound on what count can be while this interval is still in play. And then the final case, which is case 3, ending an interval, all we have to do is search for 1. What is the location of the first interval, or the starting point of the interval? And that's just stored in E3. Once I have that location, I can search my map for the number of trees chopped at that point in time. So that's just going to end up being this value right here. So this is the number of trees chopped at this point in time. So if I add to it E2, I will be exactly recovering this value. So this was the number of trees chopped when I added the value to my multiset. That's this value right here. So this value plus E2 comes out to the original value I added to my multiset. So if I find it and then I erase it, then I've removed this interval from my multiset, and it's no longer acting as a constraint on the trees that I'm allowed to chop. Then all that's left is to print out the count, and that completes our program.